Okay, we're looking at improper integrals. Basically, it's just like integration that you've already learned. We've talked about definite integrals. So when you are going from a certain value of x to another value of x, indefinite, then we don't know those indices and we know that there's a constant term. Now, improper is just that we are basically our boundary, one or both of them, is infinity, or there's a point of discontinuity or an asymptote in the graph, so it's not a continuous graph. So for today's lesson, we're looking at continuous functions where we are trying to find the integral from 1 to infinity, basically. So here's a graph of 1 over x squared. This we were just looking for positive x values. So 1 over x squared, you could have negative x values, but we're not showing that part of the graph because we're wanting to know what happens as t approaches positive infinity. So you can see on the graph we've actually just put a t here, okay? That's arbitrary, right? So if we're finding the integral of f of x from 1 to t, it's really equivalent to the area underneath the curve there. But t could be all the way out here or further. Okay, so first part here says determine the area under the curve from 1 to t. So that would mean, in this case, because it's a positive function, the area will be the integral of 1 over x squared dx from x equals 1 to t. That's going to be negative 1 over x, 1 to t. So that's going to be negative 1 over t minus negative 1 over 1. So that's really plus 1. So 1 minus 1 over t is how I would show that. Okay. Then if we're given the t value, we can just substitute in. As long as we're starting from x equals 1. So now area will, from 1 to 2 will be 1 minus 1 half. So here t is 2. Here t is 3. So a equals 1 minus 1 third. Okay. Now what happens as t goes to infinity? Okay, so x on a graph, that really means we're basically using t for our index rather than infinity. It's proper form. So here we want basically, so this is saying t is approaching infinity. So really what we're doing is the area will be the limit as t approaches infinity of 1 minus 1 over t. 1 is constant. We know if the denominator is approaching infinity, the numerator is a constant. That's going to be 1 over infinity, which is basically 0, which is 1. Okay, so the area under the curve, 1 over x squared, from 1 to infinity forever is equal to 1. It's going to help, these improper integrals will help with determining convergence, as well as splitting it up to actually find area under curves that do have asymptotes. Okay, so some properties. Okay, so basically positive continuous function starting at an a value, okay, going to infinity. That's really what the integral looks like, but we're going to show it as a limit so that the infinite symbol is not in your integration sign. Okay, so that's all that the difference is. If it's going from negative infinity to a certain, in this case, b value, then a is going to approach negative infinity, and that's going to be a in as your lower index. And then if they go to negative and positive infinity, then really you're splitting it up. Negative infinity, a approaches negative infinity here, and positive infinity here. So you kind of split it into two parts. C would be an actual value. Okay. So just know that. If you know that it's symmetrical, then you can simplify it a little bit, actually. So this one here, remember, if an even function, if a function is even, then f of negative x will equal f of x. So if you take a look here, 1 over negative x squared plus 1 is equal to 1 over x squared plus 1. So that means it is an even function. It's symmetrical about the y-axis. So we can actually split this up into two parts, right? To the left of the y-axis, to the right, they're going to be equal. So we might as well go 2 times the integral from 0 to infinity. And then let's show this in proper form. So that's going to be the limit as, let's use t like we did before. Okay, and we're doubling it because it's symmetrical about the y-axis. All right, so 2 times. So the limit, as t goes to infinity, the integral of 1 over x squared plus 1. So look on in your formula booklet. That's going to be inverse tan or arctan. IB uses arctan, so why don't we use that? So arctan of x, 0 to t. That's going to be arctan t minus arctan of 0. Okay, so arctan of 0 is 0, right? So when do you get a tan value of 0? The angle is 0 in radians. As t, so actually I'm going to show it like this. Okay, so now as t goes to infinity, think about your tan graph. Okay, arctan we defined between negative pi over 2 and positive pi over 2. That was back from Math 30-1 where we talked about that. So when arctan is approaching when t is approaching positive infinity, what's the angle here? That's pi over 2. So this is going to be 2 times pi over 2, which is pi. Okay. So next one will be limit as t approaches infinity from 0 to t over of 2x squared plus 4x plus 3 dx. Okay, so substitution, we substituted the denominator, taking the derivative would be 2x plus 4, not going to help us out. Let's factor it. I think we'll use partial fractions, so that is going to be x plus 3 times x plus 1. So a over x plus 3 plus b over x plus 1. So 2 equals a times x plus 1 plus b times x plus 3. 2 equals ax plus a plus bx plus 3b. All right, so now there's no x terms on the left, so 0 equals a plus b. Constant term is 2, that's going to be a plus 3b. Eliminate the a's. we get b equals 1, so a equals -1. Okay. So that's going to be, what did I just say? A was -1, and b was 1. Okay, then integrate that. That's going to be negative ln of x plus 3 plus ln of x plus 1. Just use a square bracket. Set. From 0 to t. Okay, so now actually we can simplify this before I substitute t in using your log laws. You don't need the absolute value anymore because t is going to positive infinity and you're adding 3. So those will be positive. So this is the same as ln of x plus 1 over x plus 3 because that's subtracting from 0 to t. Now we can substitute in. So that would be ln of t plus 1 over t plus 3 minus ln of 0 plus 1 over 0 plus 3. What brackets, this won't matter. Now, so that's going to be when t goes to infinity, this will approach 1. Okay, so here, this is going to approach 1. Not ln of that, it'll be ln of 1, right? So this will end up being ln of 1 minus ln of 1/3. Ln of 1 is 0, so negative ln of 1/3, which is the same as ln of 3. Okay. And that's where we're going to stop for today. And then improper integrals with discontinuities will continue in the next video.